So looking at the BSEN 60898 circuit breaker, we tend to have a love affair with these in the electrical industry. Many advantages to use them, one or two disadvantages. So the circuit breakers themselves run slightly different amp ratings. So we don't have a 5, we have a 6, 16, 20 and 32, very similar to what we saw before with the 5, 15, 20 and 30 for all other devices. We also have now a letter coding against the circuit breaker, these being in this case B6, 16s, B20 and B32. So all B-type circuit breakers. We can also have C-type circuit breakers and D-type circuit breakers. We'll go into some detail in the course about the design and selecting either B's, C's or D's, but just quickly, domestically, you'd have a B-type circuit breaker where there's lots of inductive loads, such as a commercial office. You'd probably have a C-type circuit breaker where you have highly inductive loads like welding equipment, some air conditioning units. You'd have a D-type circuit breaker. We'll add a little bit more detail as we move through the course on those. Circuit breakers also have a fusing factor of 1.5 or less. Manufacturers will tell you exactly the fusing factor for those, so a more precise device than a rewirable fuse. Characteristics of the fuse have been set by the manufacturer, and we cannot tamper with these in any way. So in other words, it's a sealed unit, meaning that once it's operated, the device will go into the off position. Fine, the fault has been cleared. We should be able to reset that. We will look at in a set of notes about the prospective fault current that these can clear and clear safely. There is a case that sometimes if it's a massive fault current that these have had to clear, that the actual device would need to be replaced. That's something that industry teams to ignore, the fact that they always believe that a circuit breaker can be just reset. There is an instance where they need to be replaced because of the amount of fault current they have cleared. We'll cover that in a set of notes in the classroom. Circuit breaker has physical moving parts, therefore requires to be functionally tested. So in other words, you must turn your breaker from the on position to the off, see the circuit go off and re-energize it to prove functionality. In other words, it actually turns on and off. We've got a clear-sided circuit breaker here, and we can see two other features that we'll discuss in the classroom. It has a bimetal strip and a coil here. And we've seen in previous studies in the classroom that a conductor carrying current will create a magnetic field around it. If we put that into a coil, okay, we increase the strength of the magnetic field, and we use both the bimetal strip and the fact that a conductor will create a magnetic field within the basic principles of a circuit breaker. When you overload this circuit breaker, in other words, ask it to carry more current than it's designed to do so, it's rated for this one at 20 amps. Fusing factor would be 1.5 times that, so roughly 30 amps. But we're looking at the bimetal strip at the top here. When we ask it to carry more than its 20 amps, starts to get warm. That bimetal strip eventually over time will cause the disconnection of the circuit. Where there's a short circuit of negligible impedance in circuit, the massive current creates a massive magnetic field here. So the circuit breaker could be carrying hundreds or thousands of amps for a small duration, creates a massive magnetic field, causing the mechanism to operate.